diameter of 257 for Mortaza's first sample. I made the Excel file. Okay, here you see the name of the samples. We have I just made the name similar to the concentration that we have applied. The reference one is without any melamine, M1, M2, M3 till M10 with melamine, after melamine injection. From the figures that I sent you yesterday, I wrote the peaks here, lambda peak for each one.
Yes.
Okay? And it is the concentration. The reference one, there is no melamine, so concentration of melamine is 0. The next one, the concentration is 0.01 ppb. ppb means a percent per billion. ppb, very low concentration. So your experiment is done with a very low concentration. I wrote the concentrations here, and here it is the delta lambda. What is delta lambda? Delta lambda means the difference between the lambda and this reference peak. This is the reference peak. For example, here it is 560, here is 565, it is minus 5.
Yes.
True?
Yes.
Here is 570, here is, this one is 565. So if you see, I wrote a function here, B4 minus B2. It is delta lambda.
Yes.
Yeah, delta lambda. And I calculate delta lambda for all of them. Okay,
Yes.
true? Now, the next step is plotting a figure. These are the concentrations and these are the delta lambda. But I omit some not useful delta. For example, this minus 5 is not logical. So I cleaned this row of data. Okay? Or, for example, for some data we had blue shift. I also omitted them. So here, for example, I calculated here, but I could add this one too. I didn't add. I could add it and I will correct it. Let's do it together. You can see that again. This is the concentration because it is still red shift. I included in the data.
Yes. Yes.
And it is 20. Okay?
Yes.
Now, I do it again in order to see. I will delete it. And you see. I select this part. I go to insert. I come to the scatter. And I plot the dots for this plot. Okay? Just dots. I go to this part. Here you see the trend line. I tick it. You see the trend line.
Yes.
Then I open more options in trend line. Come down, I tick display equation on chart and display R squared value on chart. You see here, I just make it bold and larger. You see, this is the equation that fits this graph. Yeah. The slope of the graph is very important for us, and it means sensitivity. So because I changed something, I need to correct this one. The sensitivity is 317 point this. Okay? This is the sensitivity. That's something that is very important for us. Okay? This one is a standard.
Why this slope equals sensitivity?
Because we said sensitivity is delta lambda divided by
No, if I want to extend
delta
this,
C. Because what?
if I want
This
to
this
extend this column, what
this
the
is
relation?
delta lambda. This is concentration.
Yes.
And we know delta lambda divided by concentration. Delta concentration is sensitivity.
معادلة sensitivity.
وانا مين جت المعادلة؟ Where this equation come from?
Yes. Okay. So this is very important for us to see how the difference can be. I forgot exactly what I wanted to say. Now, the next important factor is a standard error that we should calculate. There is one Excel function, STYX. You just choose your column X and Y. This is X, this is Y here, and it calculates for you a standard error. Okay, if you have a slope and a standard error, you can calculate LOD and LOQ.
What is the LOD mean?
LOD
In
is
physical.
limit of detection. I wrote here for you.
Yes.
I will give this to you. I will give these files to you.
And why it
here.
is important?
This is important for sensors. When we are fabricating a sensor, there are some parameters that we need to calculate. One is sensitivity. How much sensitive our sensor is to the, for example, target that we are applying here. How much sensitive? The next one is LOD, limit of detection. Limit of detection here, it has been explained. Limit of detection, lowest concentration of the analyte that can be detected. And limit of quantification, lowest concentration that can be quantified. With the accuracy of 95%. This is it,
accurate.
yeah. With this accuracy, we can predict. For example, you don't know, you have some melamine, you don't know if you can detect it or not. If you detect it, if its concentration is higher than limit of detection, you can detect it.
Yes.
If your concentration is less than limit of detection, your sensor can't detect it.
Yes. Yes.
If the concentration is higher than limit of quantification, again, you can detect and quantify it. You can say, for example, how much is the there is melamine, how
Yes.
much is there melamine?
Yes.
I mean, how much is its weight?
Yes. It is يعني
Yeah.
in the range.
We say, for example, 2 gram of melamine is present here. We quantify it. We tell a number for that. When the concentration of, for example, you are doing some real experiments inside of the infant milk, yeah. If the concentration of melamine is higher than limit of detection, you can understand that there is some melamine there, but maybe you don't know exactly how much melamine you can find there. But if it is higher than limit of quantification, both, you understand that there is melamine,
Yes.
how much of melamine you can find there.
Yes.
Okay, that one is that, and here you see the formula. Formula, you see here, for limit of detection is 3.3 times a standard error divided by a slope or sensitivity, and this one is 10 times of this standard error divided by sensitivity. So here, these are the most important results of your sample 1, that is 200. For each of them, we have the same calculations.
And we get the higher sensing, just the higher sensing.
The highest one is for 200. I just want to replace with new data here, because I changed something. I changed it. Okay, you see here, this is the sensitivity slope. Number 1 is for the first sample. The next one, 2, is for the next sample. You see 4 dots here.
Yes.
The sensitivity is coming down and decreasing by increasing the size of the polymer.
Yes.
And here you see the limit of detection, here you see the LOQ. And
Inverse limit of detection, inverse the sensitivity.
of course, the higher the sensitivity, it is clear,
Yes.
the less amount of melamine you can detect.
Yes.
Yeah?
Yes.
Okay, and That's it. And just pay attention to the number. The unit of the sensitivity is nanometer divided by ppb. So for each change in the concentration, for each ppb, we have a 317 nanometer shift. It is very high. It is really high.
Please repeat this.
Yes. سلام علیزاده هیچ ممشن بباس
Goya Vazni.
Doctor, please repeat.
It means that for changing the concentration in an amount of 1 ppb,
Yes.
you see 317 nanometer shift. It is so high. ppb is a very small amount. I wrote here the amount of the, how much is the ppb, you see here.
This shift in lambda.
In the lambda peak.
In lambda.
Yeah, exactly. And it is very high. So it shows that this sensor is really high sensitive.
Yes.
Really high sensitive. But if you go to the other ones, you see that this number is decreasing a lot. For 420, that for you is higher than double layer. But it is still high, but very lower than 200. For you, this is the highest sensitivity that you have obtained. For each ppm,
Doctor,
ppb,
we use the same concentration in two cases.
yes, everything is the same. In this one, it is 154 nanometer for per ppb. And this one 57, and this one 53. So everything is logical.
Alhamdulillah.
Every behavior that we have seen is logical, but it is different from what I was expected. I was expecting that 200, 1200 has the highest sensitivity because it was so organized.
Yes.
It was my expectation, but it says that no,
Yes.
because the nanoparticles are so far from each other, because we have big polymers, the electric field, electromagnetic field of each nanoparticle cannot interfere with each other in a good way, so the sensitivity is lower. In your case, fortunately, we have the same result. The less distance, higher sensitivity. In the double layer, you have smaller nanoparticles, but they are far from each other. But in one layer, you have nanoparticles that are near to each other. So the conclusion of both of your works is saying something very important, that whenever we want to fabricate a very high sensitive LSPR sensor, we need to design some structures, some samples that the distance of the nanoparticles are not so much.
No, sir.
I really like the
Yes,
results,
yes,
really,
yes.
because your results is the complementary of his
Alhamdulillah.
result, and everything says that everything was okay.
Alhamdulillah.
I am so happy for that. Just
Why-
for future,
Yes.
they are going to ask you, what are you suggesting for future? Okay, this is what you are going to
We
write in
suggest-
chapter 4. You should say one of the suggestions to use an spectrophotometer that it has higher sensitivity.
Yes.
Use smaller steps. Your steps were 5 nanometer. If we were using some other spectrometers that its sensitivity is higher, or even the same
There is
spectrometer, less than 1 nanometer, so our results could be more accurate.
Yes.
It is one suggestion for future work. Another suggestion for future work is going even smaller than 200. Even we can fabricate.
100.
Yeah, make our spheres.
we can
We can
We cannot
make.
tell.
We
Yes.
can make. We can
Yes.
make. It is not easy. The easiest one is larger than 200. But
Why?
if we try
It is
fabricating,
Polymerization.
it is because of synthesizing. Making them smaller is a little bit more difficult. But one of our students did it. Maliha did it. Maliha Hanfar. So if we want to
At which
fabricate
range approximately?
less than 100, she made.
In this case,
Less than
we
100?
should.
Yeah, she fabricated.
In this case, we should be change the concentration of gold. We use
Concentration or thickness?
thickness.
Yes, we can. Very good question. And now we should change the thickness in that case.
Yes.
The smaller, we should change the thickness. Another suggestion for future works for both of you, changing the thickness of the gold that we have deposited in all of
Less
the
than
works.
or more than
We should try.
optimal.
My guess is better results for a smaller size.
we do deposition.
No, 50
50 now.
nanometer.
Around 50.
Both of you, for all your samples, you have deposited 50
50.
nanometer.
Doctor, we used 20 nanometer, but the result not good.
Yes.
Do you remember that?
Yes. The result was not good, but because you have used it for, I don't remember.
You say not have the big.
Really?
Yes.
So again, it's another project. Someone should come, continue your works, choose 200 and smaller, and then optimize different thickness of gold
Yes.
gold layer, gold deposition. So
B, C. شانس.
exactly. To
مثلا
see which one is
یک
better.
یک project میشه مثلا دویست با changing thickness of nanoparticle of gold
Exactly.
and compare between this.
Exactly. It is the next project
Doctor, what is the
that we can work on it.
what is the limit of this thickness?
It depends on the machine that we are using to do magnetron sputtering.
يعني
The lowest thickness that this machine can deposit is around 2 nanometer. But it is so low because the amount of the gold is so low, because in some other works we have tried that. Actually there is nothing that we can detect when it is very low. But my guess is maybe 50 is the best answer. Who knows?
Maybe.
But I think maybe the best answer is from 40 to 80, not large, not
The
bigger, not smaller.
The diameter. Continue.
Come finish.
The diameter of the sphere of PMMA. How many?
For us, not smaller than 50
50.
nanometer.
Then if it is 50 nanometer and gold 50 nanometer, how many?
No, it can't be. In that case, we need to reduce the size of the gold, the thickness
No,
of the gold.
if
The
we, the
thickness of-
sphere of nanoparticle
Yeah, I know.
about 50.
In that case, 50 for gold is a lot.
We deposit 50 nanometer.
Now you deposit it, but
If we can deposit gold, the less than
we should deposit gold at least half of the diameter.
half of diameter.
Because
If it will be 50, we deposit
25 at the
25.
end.